So let me start the session titled Cloud Native Scalability for Internet Developer Platforms. And so my name is Hiroshi Hayakawa. I'm a platform engineer working for LY Corporation's private cloud division. And LY Corporation, LY Corporation is one of the largest internet company in Japan and offering a wide variety of services. For example, communication apps, internet portal, news media, and e-commerce, and so on. So we have been operating platforms at a large scale for a long time. So I hope to share that experience as well. And I contribute to CNCF platform community group. And I have written books on Kubernetes in Japanese. And I love building DIY keyboards. And by the way, this is a current setup on my desktop. Pretty cool, right? So today, I'd like to talk you about the scalability challenges we faced in our internet platform. Now, I've divided my presentation into 4 main parts. First, let me start by giving you some background, such as what the platform is, its capabilities, and an overview of its architecture. And next, we'll dive into our 5-year scalability journey, the challenges we faced, and how we solved them, and what we learned. And then we are still working on making the platform more scalable. So I'll introduce our plan for further improvement. And finally, we'll wrap things up with conclusions, summarizing the key takeaways. All right, so let's get started with the background. So first, I'd like to share what our platform is to provide you with some context for this session. It's a platform as a service for web applications like Heroku or Cloud Foundry. And it allows developers to run their applications with a few simple commands. The first command on this screen creates an application with a specified container images. After a few seconds, the application becomes ready and becomes available with allocated URL without any extra effort from developers. And this is a high-level architecture of the platform. It's composed of a single control plane cluster and multiple workload clusters. And these Kubernetes clusters form one large logical cluster. The control plane cluster handles all operations from developers. So if a developer requests a cluster to deploy an application, the cluster scheduler running on it selects a workload cluster and deploys the application on the workload cluster. And the cluster scheduler also creates resources for exporting the application, such as ingress and services, and also creates a DNS record on core DNS running outside of the platform. And then requests from users are routed to the cluster where the application runs, and through name resolution. And thanks to this architecture, the platform is now used at the scale shown in these numbers. It has grown to this size in about 6 years from design phases, and I believe we have achieved our initial goals. Of course, we faced a number of challenges as the scale grew. So in this session, I will pick up 4 insightful challenges. And next session, we will dive into each of these challenges. So let's dive into the challenges. Yeah, our team's first concern was how to host the requested number of applications using Kubernetes. Yes, we considered this in the design phase because the estimated number of applications was unlike we had experienced before. So ensuring that all developers in the company could use the platform was the most important requirement. And we considered two approaches to realize this requirement. One is scaling up a single cluster, and the other is building a single logical cluster with multiple clusters. And as I already mentioned, our platform adopts a multi-cluster approach. However, considering the sessions at KubeCon London held in April, it seems that these are use cases of both approaches. So let me explain why we choose the multi-cluster approach by comparing the pros and cons of each approach. First, in terms of resource efficiency and cost of cluster management, I think a single cluster is a winner. With a multi-cluster setup, there are more clusters to manage, and the overhead from system components increases with the number of clusters. Additionally, developing components like our cluster scheduler is necessary to form a logical cluster with integrating with multiple clusters. But however, in our case, we already had experience managing a number of clusters by providing internal Kubernetes as a service like GKE. So we didn't have to worry about management cost. And compared to ordinary situations, the advantage of multi-cluster approach is that each workload cluster works as a boundary that enforces the impact of, encloses the impact of failures. Additionally, it allows us to keep each cluster not so large. And this makes things easier and reduces unexpected issues typical for cluster add-ons. So based on this point, we can expect to scale our logical cluster in a predictable and safe manner. Finally, let's look at the functional aspects. With a multi-cluster setup, some basic Kubernetes functionalities may need to be compromised. For example, developers cannot use standard Kubernetes resources like deployments or pods and so on, and because they are wrapped with the control plane cluster. And an additional solution is required to enable networking between pods across workload clusters. However, in our case, we aim to provide a platform as a service experience to developers, so these requirements were not necessary for us. So here is an overview of our comparison between the two approaches. But as you know, we decided to use a multi-cluster setup, as I mentioned in the previous section. And this decision was made by considering the platform's requirement and our team's skill set. And I believe the results would have been different depending on the organizations. Yep. On a different note, let me introduce how we used workload isolation in multi-cluster setup to prevent the noisy data problems. This tree map represents the distribution of resource consumption of individual applications. And it shows the distribution trends to be divided into two characteristics. A few applications that consume a large number of resources, and a large number of applications that consume small amount of resources. And I believe that this is likely the case in many organizations. So considering these trends, we isolate applications with high resource consumption into dedicated workload clusters because they are more likely to cause noisy neighbor problem. Meanwhile, smaller applications are placed in shared clusters, and this approach allows us to isolate only the necessary workloads without sacrificing resource efficiency. And this approach is based on the same principles in designing multi-tenant SaaS applications. If you are interested, please refer to this book. In this book, we can see three concepts of multi-tenant architecture: pool, silo, and tenant context. In the pool model, multiple tenants share resources with isolation happening at the application layer. And the silo means each tenant has dedicated resources, providing stronger isolation with clear physical boundaries. In our platform, we use a mixed model of pools and silos according to the trends of resource consumption. And last one, tenant context is how we identify which tenant each, the context is how we identify which tenant each operation belongs to using tokens or similar markers. And tenant context is so important in the challenge that I will introduce later. So let me summarize what we've learned here. First, both single huge clusters and multiple clusters have their strengths and weaknesses. The best choice depends on your team's skills and requirements. Second, your isolation strategy should be based on the nature of the workloads. In our case, combining silo and pool models can help reduce the effects between applications. So let's move on to the next challenge. The second challenge is operational scalability. At this point, we were operating the platform with about 5 or more people. However, we need to establish automation in preparation for making it public to the organization. A prime example of such operational challenges is the onboarding process. That means it about the back end when developers start to use the platform. In the flow before automation, the process begins with developers requesting to create a tenant through a ticketing system. And then 2 manual operations by platform engineers are required. First, they register an authorization policy for the tenant in an authorization system called Ascens. This policy will be used for authorization later when developers create access to the API server. Next, the platform engineer creates a namespace resource for the tenant in the Git repository. The namespace is managed in a GitOps-like manner, so the namespace resource will be reflected in the control plane cluster. And once these operations are completed, the developers can send requests to the API server in the control plane cluster, and then authorization webhook in the Kube API server delegates the authorization to Athens. And as a side note, Athens is an open source software that is also a CNCF sandbox project. And it is showcased at the Airby Corporation booth, so if you are interested, please check it out. Now let's talk about the automation. We automated these manual operations step by step. First, we replaced the policy registration with a custom controller. Since each policy corresponds to a namespace, so it can be replaced with a controller that reconciles the namespace. And we continued for a while, providing onboarding experience with this flow to verify the reliability of the controller. And finally, we replaced the ticketing system with an application for onboarding. It receives a request and handles the creation of namespace in the repository. At this point, we achieved a complete self-service experience, and also the platform team is freed from manual operations. So another lesson learned from here is about how we approach automation. Instead of trying to automate everything at once, we should break workloads into parts and then replace them gradually. It's also important to apply automation at the right time when it's really needed. And this illustration shows this concept. The bottom row replaces part of things at each step, providing working solutions, instead of replace whole things as top row. So now let's next challenge. The next challenge is the scalability of the metrics pipeline. The basic structure for our metrics pipeline consists of agents running on a Kubernetes cluster, a message queue that faces those agents, and a backend behind it. The backend includes some components such as time series, databases, and query engines. When stores are metrics and allow developers to access them. This slide figures a pipeline for container resource metrics, such as CPU and memory usage. Each agent access to the kubelet on the same nodes to collect metrics, then sends to the backend through the metrics queue. The issue was that the metrics agent couldn't identify the tenant of the container just by looking at the metrics from the kubelet. In other words, the tenant context of the metrics is lost through the agent. And without tenant context, all metrics are stored in a single default tenant, which causes overloading of the default tenant. And to address this problem, we implemented an extension to the agent that enables it to identify tenant. With this enhancement, we can keep the tenant context and leverage the backend's multi-tenancy features to distribute the load to each tenant. And now, this diagram is a bit different from the previous ones. This represents the pipeline for application-specific metrics. So in this diagram, agents collect metrics directly from the exporters inside the container. Since the agent cannot dynamically identify the tenant context, each agent is configured to collect metrics only from applications in fixed tenant. And this approach helps prevent overloading the backend by distributing the metrics. However, with this approach, the agents assigned to tenants that contain extremely large applications. So because unable to handle the volume of metrics. In this case as well, identifying the tenant dynamically from each metrics works to solve the issue. We implemented another extension to the agent to enable a single agent to handle metrics from multiple tenants by identifying tenants from each metric. This allows us to switch to deploying the agents as a daemon set because each agent only needs to collect metrics from containers on the same node. Since the agents run as a daemon set, they can naturally scale as a cluster grows. So let's look at the key lessons we learned here. First, dynamically handling tenant context boosts scalability. It lets us take full advantage of multi-tenant features in technology stack we use and scale components more smoothly. Second, it's important to think about how your component can handle tenant context dynamically. This is crucial for building flexible and scalable systems. And the last one I pick up is custom controller scalability. And to avoid reconciliation conflicts, only one controller instance can reconcile same kind of resources. Therefore, even if the number of resources increases, we cannot scale out the controller. As the number of resources grows, reconciliation starts to fall behind and leading to various problems. And for now, we are addressing this by scaling up the single controller instance. In other words, we deploy the controller on a dedicated node, allocate a large amount of CPU and memory, and tune the controller to reconcile in parallel to utilize multiple cores. Now, the takeaway here remains somewhat in question. I just mentioned that scaling up controllers is the only way to ensure controller performance. But is that really true? In fact, our team is currently exploring a way to scale out controllers, and we will cover that in the next section. Now, in the third section, I'd like to introduce the challenges we are currently facing and how we are approaching them. The challenge we are facing now is the scalability of the control plane cluster. Even in a multi-cluster setup, we cannot increase the number of control plane clusters. So as the platform further grows, this cluster will become a bottleneck. Then we can break down the scalability challenges of the control plane cluster into 3 issues as shown on this slide. First is the spike in API server memory usage when handling list requests. Second is the growth of etcd data size. And the last one is the issue mentioned in the previous section, the inability to scale out custom controllers. The issue of API server memory consumption is already being addressed by the upstream Kubernetes community. The solution is replacing the bulk response to list requests with streaming. From Kubernetes version 1.33, this feature is enabled by default, and it can be used without any changes on the client side. And to address the issue of etcd data size, we are planning to move some certain types of resources to workload clusters. By leveraging the aggregation layer and extension point in Kubernetes, clients can operate on external data as if it were in a Kube API server. And this allows us to distribute resources across workload clusters. Lastly, to tackle the issue of controller scalability, we are considering using an open source project called Kubernetes controller sharding. This approach assigns resources to multiple shards and runs separate controllers for each shard. While Kubernetes controller sharding is still under active development, so we are aiming to contribute to the project and work together with the community to help solve this challenge. There was a session about the controller sharding at KubeCon London, so if you are interested, be sure to check it out. Now, to wrap up the session, I'd like to summarize the key lessons we've learned. That said, we have encountered many different lessons, so it's a bit hard to sum up in just one sentence. So the slides are available for download, so please take a look at each of the lessons learned pages. And yeah, the journey of scalability probably has no end, so let's enjoy the journey itself. And finally, I'd like to express my gratitude for cloud-native technologies and the community. In addition to Kubernetes, there are numerous projects that support the success of platform engineering. So maybe we have time for one question. So do you have any questions? Please raise your hand. Okay. Yeah.
Thank you for your presentation. So, in previous session, I see some open source related to how to schedule applications on multiple clusters, like Kubernetes or something. So, do you have any such system or software for controlling application on multiple cluster side?
We make the cluster scheduler by us, it's ourselves, but we are now building a new platform. We have a booth introducing Flava. We are building PaaS services on top of Flava, and we are now reconsidering about which technologies use on the new platform.
Okay.
Yeah, makes sense? Yeah.
Thank you.
So, yeah, feel free to. Thank you so much. Thank you so much.